Hi everyone, and thank you for attending today's webinar, Deep Reinforcement Learning and Robotics with NVIDIA Jetson, hosted by Dustin Franklin. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple application widgets. All of the widgets, as well as the slide area, are resizable and movable, so feel free to move them around to get the most out of your desktop space. If you have any questions during the webinar, please submit them through the Q&A widget. We'll try to cover as many questions as possible during the Q&A portion, but if there's any we don't get to, please post them on the forum to keep the conversation going. Be sure to check out the resource list for links to the developer site, forums, wiki, and more. And if you run into any technical issues during the webinar, you can always find answers to some common questions located in the Help widget at the bottom of your screen. An on-demand version of the webinar, as well as the slide deck, will be available approximately 1 day after the webinar and can be accessed using the same audience link that was sent to you earlier. And with that, let's get started.
Hey everyone, thanks for making time and joining us today. We're going to talk about deploying AI in robotics and autonomous machines and using deep reinforcement learning with NVIDIA Jetson and GPUs. We've got lots in store for you today, so let's get started a while. Here's what we'll be covering today. First, we're going to share some of the latest news about Jetson, and we'll introduce the concepts behind reinforcement learning. Then we'll dig into our first reinforcement learning agents using PyTorch and the OpenAI Gym. Next, we'll demo a C++ API for Python and PyTorch, so our agents can be integrated with simulators and robots. We're also going to talk about the latest research and discuss how it can be transitioned from virtual environments to physical systems operating in the real world. So why are we here? Recent leaps forward in compute horsepower and AI have brought on a new era in robotics and autonomous machines. Enhanced computer vision and perception are being applied to make robots much more capable and robust in practice, and they're being deployed across practically every industry. Last mile delivery is bringing goods and services directly to consumers faster and more efficiently. Robots in factories and warehouses are optimizing assembly and logistics, reducing the costs of producing goods. Precision agriculture is reforming the widespread use of chemicals used to grow our food. Autonomous drones are being deployed for industrial inspection of our energy grid and monitoring our natural resources. Many of these machines are deploying the latest technology from NVIDIA to operate remotely with onboard compute at what's called the edge. Due to their limited connectivity and the latency-sensitive requirements inherent in being mobile, they need advanced levels of autonomy to operate effectively and safely in their environments, and require the most capable onboard processing available that can meet their demanding computational needs. Some of you may already be familiar with our small form factor embedded computers, Jetson TX1 and TX2. They're complete system-on-modules including ARM CPU, memory, I/O, and integrated NVIDIA GPU capable of delivering over a teraflop of AI performance to the edge. They consume about 10 watts of power and are able to be deployed into a wide range of devices, typically used for real-time inferencing and computer vision. This spring, we introduced Jetson TX2i for industrial environments. It's got wider qualifications for things like shock and vibration, thermals, and ECC memory. Jetson TX2i has an extended temperature range of -40 to 85 degrees C and a 10-year operating lifetime. It's also pin-compatible with the existing TX1 and TX2 modules and runs the same Jetpack software. If you're operating in an industrial environment, you can easily drop TX2i into existing Jetson applications and benefit from its enhanced ruggedization. Recently, we announced Jetson XAVIER, our latest AI supercomputer on module. Jetson XAVIER is an entirely new class of processor in the market. It brings 30 teraops of mixed precision INT8, FP16, FP32 compute, and 30 watts of power. It's 100 by 87 millimeters, and it's got a 512-core Volta GPU with support for NVIDIA Tensor Cores, along with 2 NVIDIA Deep Learning Accelerator engines for offloading inference. There's an 8-core ARM CPU, 16 gigabytes of 256-bit memory with 137 gigabytes per second of memory bandwidth, a new hardware vision accelerator engine, multiple 4K P60 video codecs, and just for 8 MIPI cameras and PCIe Gen 4. Like its predecessors, it runs Linux and Jetpack, and Jetson XAVIER dynamically scales between 10, 15, and 30 watts of power consumption depending on workload. Jetson XAVIER represents a great leap forward in capabilities for autonomous machines and edge devices. It's got over 20 times the compute and more than 10 times the energy efficiency of Jetson TX2. Its Tensor Core GPU alone has 8 times the flops, not to mention its CPU with double the performance as before and more than double the memory bandwidth. This huge boost in performance will enable next-gen robots with the compute horsepower they need to accomplish full autonomy. Jetson XAVIER can host the end-to-end AI pipeline and dozens of real-time algorithms concurrently for performing things like sensor fusion, inferencing and perception, path planning, navigation, and HD mapping. To keep its compute resources fed with data, Jetson XAVIER offers a ton of I/O, including more than 30 gigabytes per second of PCIe bandwidth. It's one of the first devices to offer PCIe Gen 4, and some of its PCIe controllers also support endpoint mode in addition to root complex, so you can interconnect multiple Jetson XAVIERs together with RDMA or into other systems. It supports more MIPI CSI camera lanes than before, now 16 lanes at 2.5 gigabits per second each, enough for up to 8 CSI X2 cameras or up to 4 CSI X4 cameras. There's additional USB 3 ports, and it can drive 3 4K P60 displays simultaneously via DisplayPort or HDMI. It also includes the traditional embedded I/Os like I2C, SPI, GPIO, and CAN bus. Like with TX1 and TX2, we created a developer kit for Jetson XAVIER. It uses standard plug-and-play connectors and makes it easy to get started with. It has a PCIe slot, 3 USB 3 ports, 2 of them USB-Cs with DisplayPort, HDMI, and headers for the MIPI cameras and GPIO. It has 2 sites that can be populated with M.2 modules for wireless and NVMe storage. The dev kit includes the module, reference carrier board, power supply, and heatsink. The carrier has been shrunk from previous generations and now shares a similar footprint to the module. The Jetson XAVIER dev kit will be shipping in August for early access and October for general access. Developers who are already working with TX1 or TX2 and are developing an autonomous machine using Jetpack may qualify for early access by signing up to be notified on our website and completing our survey when we send it out. In addition to Jetson XAVIER, we've announced NVIDIA Isaac, our platform for accelerated robotics development. The Isaac SDK is a collection of libraries, drivers, APIs, and other tools that'll make it easy to add AI into next-generation robots for perception, navigation, and manipulation. Isaac has high-fidelity simulation for training AI in virtual environments, and the runtime components target Jetson for deployment and includes various algorithms and building blocks for implementing autonomous machines. Isaac aims to train the robot in synthetic environments nearly indistinguishable from reality, where the AI can be developed safely and without causing any damage. It's also useful for verifying corner cases, which may be hard to find and reproduce in the real world. There's a shared software stack and hardware-in-the-loop simulation for Jetson, so that the robot always thinks it's operating in the real environment. The algorithms are accelerated with CUDA and TensorRT underneath, so they're low overhead and perform optimally. Isaac includes a robust component messaging framework that allows algorithms to be chained together into a pipeline and partitioned in safe and secure ways. To find out more about Isaac, visit our website and register to be notified when we roll out upcoming releases. The AI solutions that Jetpack and Isaac enable frequently utilize various deep learning frameworks for creating neural network models. NVIDIA maintains support across the deep learning ecosystem, having optimized CUDA and cuDNN backends integrated into every major framework, including Caffe, Caffe2, Microsoft CNTK, MXNet, TensorFlow, and PyTorch. Models trained with these frameworks are then deployed either with TensorRT or natively onto Jetson. In this webinar, we're going to use PYTORCH predominantly to implement the reinforcement learning algorithms. Due to its close integration with cuDNN and first-class GPU support, the performance is such that we can run the PYTORCH code all natively onboard Jetson TX1 or TX2, which adds to the elegance of the solution of the robot being able to learn in situ onboard the real hardware being deployed. To get started today developing and deploying your own AI-powered applications with Jetson, there's a number of open resources that we've made available to the community. Our developer portal is the main source of downloads and documentation on the Jetson platform. Every Jetpack and L4T release can be found there, in addition to thousands of pages of docs on the hardware and software. Technical support is provided through the DevTalk forums, where you can interact with fellow developers and staff from NVIDIA. We also have the wiki on eLinux, where we post guides and recipes that otherwise aren't covered in the official documentation. If you haven't already, register as a developer through our site, so you can post to the forums, access the docs, and stay up to date with the latest. One open source tutorial that we've developed for the community is what we call 2 Days to a Demo, which some of you may already be familiar with from previous webinars. It's an end-to-end guide to getting started with training and deploying your own deep learning models using our interactive digits training framework and TensorRT for accelerated inferencing on board Jetson. It contains step-by-step guides for image recognition, object detection, and segmentation vision primitives, which can in turn be retrained on your own subject matter and integrated into AI-powered applications. It's called 2 Days to a Demo because you can follow it in roughly 2 days to make your own deep learning app. The original 2 Days to a Demo is based on what's called supervised learning, where pre-labeled datasets are used to train the networks and inform them of the correct outputs. After training the models to convergence, they're able to generalize at runtime and infer results on data that they haven't seen before. However, there are other kinds of machine learning in use besides just supervised learning. In fact, there's an entire spectrum of learning which ranges from supervised to fully unsupervised. The topic of this webinar, reinforcement learning, lies somewhere in the middle, where the developer sets up the environment with a reward function which then guides the agent based on its current performance. Reinforcement and unsupervised learning systems are able to be trained in situ in their environments and adapt in real time, which is called online learning. Reinforcement learning works by integrating feedback from the reward function to train the network. In epsilon-greedy algorithms like deep Q-learning, their strategy is to maximize their potential future reward. Based on these predictions, they choose the agent's optimal action given its current state or input, in this case the pixel array captured from the screen or camera. During training, each time the agent performs an action, it's assessed a reward from the environment, and this process is repeated until convergence and the desired behavior is attained. The benefits of reinforcement learning are that it can learn to perform complex, intuitive behaviors and tasks that would not necessarily be easy to generate large amounts of pre-labeled training data for, like in supervised learning. For example, like in motion control of a robotic arm assembling parts, or locomotion of a humanoid that has many degrees of freedom and a high-dimensional state space. Reinforcement learning agents are able to explore their environments in search of the optimal behaviors. Reinforcement learning has roots in not just machine learning, but also in psychology, and it's one common way that many animals and humans are able to learn. For example, training a dog, or how babies learn to walk from falling down until they're able to stand on their own. It takes both positive and negative reinforcement to train an agent effectively. You also have to be careful how to reward agents for the correct thing. Otherwise, epsilon-greedy algorithms in particular can develop unwanted habits to hoard extra reward, a trait also shared sometimes by animals and humans. For this webinar, we have a new version of 2 Days to a Demo geared specifically for reinforcement learning. As mentioned, this edition of the tutorial starts out playing in the OpenAI gym to make sure that the reinforcement algorithms are learning properly. Provided is an open source C++ API to the reinforcement algorithms, which are implemented in Python using PyTorch. With the C API, it's much easier to integrate into existing robots and devices, which are predominantly based in C++ or ROS, the robot operating system. This 2 days to a demo also provides virtual scenarios for the robot to learn in simulation and gradually increases the complexity of tasks to improve the success of training the networks. Next, we're going to walk through the tutorial and the code in a screencast from the Jetson. Here we are on the desktop of a Jetson TX2 dev kit, freshly flashed with Jetpack 3.2, although you can also run this tutorial on a x86 PC with an NVIDIA discrete GPU attached that has Ubuntu 16.04 installed. Here's where you can find the contents of the Deep Reinforcement Learning tutorial and the GitHub repo with the source code. We'll provide a link to it in your webinar viewer. It includes all the instructions to follow along, and the setup of it's mostly scripted. We'll start with deep Q-learning and some basic environments from the OpenAI Gym to verify that our RL algorithm's learning properly. Then we'll start using the C++ API and some natively compiled samples to confirm our agent's still working as expected outside of Python. Then we'll integrate with the Gazebo Robotics simulator in 3D, which we have a couple environments created for. The software stack will end up being fairly significant and be able to output the robot's actions from the raw sensor data. For continuous control, we'll end up introducing some newer reinforcement learning algorithms like Actor Critic and A3C. These have the advantage of being able to output values directly as opposed to choosing a single discrete action and being able to output multiple values simultaneously, which is important for robots that have many degrees of freedom to control. So after cloning the repo and building it from source according to the included instructions, we have a couple IPython Jupyter notebooks to familiarize ourselves with PyTorch and the Deep Q Learner. The Jupyter server is launched onboard the Jetson and is accessed interactively from the web browser. First, we're going to start with an introduction to PyTorch and how it uses CUDA for those of you who aren't already familiar. This has the added benefit of getting to verify that PyTorch is installed correctly on your Jetson with GPU acceleration enabled. Now, some of you may be wondering, why are we using PyTorch for this tutorial and not another framework like TensorFlow? Well, mainly that PyTorch builds and runs natively on Jetson with close to optimal performance, and there's a lot of existing RL code out there for it. Now, if you wanted to, you could apply the principles from this tutorial to another framework and implement it practically the same way. Okay, now back to the PyTorch notebook. The first Python command that's run in the notebook imports the PyTorch packages. Now, if there was a problem building or installing PyTorch in your system, this command will throw a bunch of errors because it's not able to find the PyTorch packages. If it doesn't say anything, you're fine and PyTorch will be able to be found. Next, let's confirm that the correct version of PyTorch was installed. It should read v0.3 because that's what this repo uses and what the build script installs. Okay, now we're going to confirm that CUDA was configured correctly in PyTorch and that the GPU is being detected at runtime. So this should print out true if PyTorch is able to access and use your GPU. Next, we're going to allocate some example PyTorch tensors, which are the main way that memory and data are passed through PyTorch. A tensor is a multidimensional vector or matrix, which typically represent inputs or outputs to the neural networks. Now, to make sure that a tensor resides in GPU memory, you call the .CUDA function on it, and then it will be marked for CUDA, and math operations that are called on that tensor will be executed using CUDA. You can see here when we print out the tensors, it's confirmed that they reside on the GPU after we call .CUDA on them. Now, instead of needing to call .CUDA on every tensor that we make, we can configure PyTorch in the script by setting up some aliases so that every tensor is allocated as a CUDA tensor. After running this snippet, you can see that this new tensor was automatically allocated on the GPU even though we didn't explicitly call .CUDA on it. Now that we've confirmed that CUDA and GPU acceleration are functional, let's test out the PyTorch NN package, which implements the neural networks using cuDNN underneath. First, import the torch.nn package. You shouldn't see any errors here if it was installed correctly. Next, we're going to allocate some randomized tensors that'll allow us to test that the network is training properly. You should be able to tell here that they've been allocated on the GPU automatically from that snippet above. Next comes the fun part. We're going to define the topology of our neural net, in this example some simple fully connected layers. To get our network model to use cuDNN, we have to call .CUDA on it in a similar way that we did with the tensors. Next, we have to define our loss function, which compares the output of the network with the expected output and informs the backpropagation of the gradients it needs to apply to the network weights. Here's the main training loop. First, we do the forward pass, which uses the network to predict what it thinks the output should be. Then we compare that to what the output actually is. This is being supervised learning. Then we compute the backwards pass and apply the gradient updates so that the network learns for next time. Now when you run this, it'll kick off a training loop which runs for 500 iterations, and each iteration it'll print out the loss, which corresponds to the current accuracy of the network. Now what you should see is that the loss starts high and gets smaller each iteration, until eventually it gets to be below 0 and then very, very small. This signifies that the network model is learning to predict the outputs correctly. Although this example model is one-dimensional and simple, it is using CUDA and cuDNN and proves that the GPU acceleration is working in PyTorch as expected. So that's the end of the Intro to PyTorch notebook. Now that we know everything's working, we're going to close this notebook and then launch another one which implements the DeepQ learner and uses the OpenAI Gym. So follow along with the instructions from the GitHub repo to launch the DQN notebook on a new Jupyter server instance running on your Jetson. It should load in your web browser like before and look like this. Now in this example, we're going to use DeepQ learning to master this pendulum balancing game called cart pull. It's 2D, and then our DQN agent will be learning from a raw pixel array captured from the screen itself and not from variables from the game like the angle of the pendulum. It'll have to learn to infer that from vision for itself. So first we start by importing some packages, including the Torch and TorchNN package that we used from the previous example. Next, we're going to create our cart pull environment from the OpenAI Gym. We're going to bring in that same snippet from last time that will make sure all the tensors are automatically allocated on the GPU. Next, we define replay memory to store the states. Then there's a mathematical explanation of DeepQ learning and the reward function that it estimates. Before, we defined the DQN model and the neural network. This time, we're doing a full 2D convolutional neural network since we're going to process a pixel array as opposed to 1D data. This is what makes it deep reinforcement learning. Next, we're going to set up the extraction of the pixel array that's captured from the screen and input to the neural network. These deep reinforcement learning methods are commonly referred to as pixels to actions. Here you should see an example of the captured screen pop up to confirm that's working. This is what the pixel array input to the network looks like. Next, we create an instance of the DQN model that we defined above and flag it to be run on the GPU. We implement a wrapper function for forward pass inferencing, which takes in the pixel array and uses the network from the DQN model to predict the action. Next comes a function that does one training pass by pulling out a batch of frames from the replay memory, doing the forward pass, and then computing the gradients that are applied to the network update. This function gets called once every training iteration. Finally is the main loop, which runs until the DQN models converged or for a set number of training iterations. During the loop, the latest frames captured from the environment and the forward pass inferencing predicts the action using the DQN model. These are then pushed into the replay memory along with the agent's reward, which in this scenario is based on how long it's been able to balance the pendulum for. The replay memory then gets used in that optimized model function that we defined before. So that's it for the training loop and the implementation of the DQN. You can go ahead and kick this off and it'll start running and printing out how long it's able to stay balanced for before the pole tips over. At first, it won't be able to stay balanced for very long, and the durations printed out will be fairly low. But as the DQN learns over time, the average of the durations will gradually increase, until it's able to balance the pole almost perpetually. Typically in this simple cart pole example, it only takes the DQN a few minutes to learn it. It's not really intended that you run this until convergence from within the notebook environment. For that, we have a separate script which you can launch from the desktop to keep an eye on. So after you see some positive signs that the DQN's learning, you can go ahead and close this notebook and terminate the Jupyter server. Okay, so we have a standalone Python script, gym-dqn.py, which essentially is the same code in it, but can be run outside of the Jupyter environment for longer runs, and has additional visualization built in to keep track of the agent's progress. You should see the application start up in a similar way as before, just now there's this graph that charts the performance of the agent over time. Okay, now if we fast forward and jump ahead a little bit, we can see the agent converging on the desired behavior and balancing the pole. In reality, this only takes a few minutes of training time on TX2 to achieve. You can see here the agent having a handful of good runs, followed by balancing the pole for quite a while. Having the DQN agent able to be successful at this entry-level cart pole example verifies to us that the algorithm's working as expected and that we can move on to the next scenario. Anytime you make changes or updates to the reinforcement learner, it's important to regression test it, starting back from the beginning with this simple example. Otherwise, it can be difficult to track down bugs later on, after we get to full 3D simulation. Next, we're going to try using a more complex environment from the OpenAI Gym, Lunar Lander V2. This environment isn't dissimilar from a drone auto-landing scenario. The goal is to have the agent land the spaceship safely between the flags, even though the terrain is randomized upon each new episode. Now at first, the agent crashes every time because it hasn't learned to fly yet. But if we fast forward a few minutes, the agent begins to learn how to fly until it first touches down, and then over time it learns how to land reliably. Now even though this lunar lander scenario is still 2D, it does demonstrate that the reinforcement learner is capable of performing more complex robotic control, in this case piloting a drone. Now, there are a number of other environments from the OpenAI Gym that you're welcome to try on your own. The command line that launches this script takes an argument that specifies the name of the environment that you can change. Okay, now that we've successfully tested our DQN agent in a couple different OpenAI Gym environments, let's make the next step and introduce the C++ API so that we can utilize it from native applications too. So we've created a library that wraps the Python scripts that implement the reinforcement learners so they can be used from C++ applications like the simulators and the real robots. The API is extensible to different reinforcement algorithms that are shared across virtual and physical environments without needing to change the user's code. A Python interpreter runs locally inside each type of reinforcement learner that in turn loads its Python script and calls it from C++. Now in the case of the DQN agent, the script isn't very different from the code that we authored earlier in the notebook. We just refactored it from being a monolithic standalone program that controlled its own main loop and control flow to being modular and event-driven via a few callback functions that the C++ library calls when it has new sensor data and wants the next action from the agent. There's also a callback defined that provides the agent with reward issued from the user's application and kicks off the next training iteration. Having the agent be modular and event-driven is important because most Python scripts you'll find are designed to operate standalone and not necessarily be called from another application, which can make them difficult to integrate with existing apps and significantly increase the latency when you're working with real-time data. In addition to refactoring the control flow of the scripts, we've added the ability to pass data back and forth between C++ and Python without additional memory copies via PYTORCH tensors that are allocated with CUDA. This means that the camera or video frames can be passed directly to the reinforcement learner. Let's take a look at what the DQN agent looks like from the C++ side of things. Here's the definition of the DQN class. It has a create function which takes in a bunch of settings along with a next action and next reward functions which get called by the user when there's new data to act on. Now there is an upgrade that we made to this DQN versus the one from the notebook. We optionally added LSTM support to its network, which you can toggle using this parameter to the create function. Recurrent LSTMs, or long short-term memory networks, are a specialization of RNNs, and when added to deep Q learning, the whole algorithm is commonly referred to as DRQN in the research, which stands for Deep Recurrent Q Learning. Now, the advantages of integrating LSTM or RNN into the network stem from the built-in memory internal to these recurrent layers. At a high level, they used loops between neurons to form a kind of working memory that aids when inferring on sequences or time series data, or as is commonly the case in robotics, when operating in a partially observable environment where the sensors are unable to maintain an omnipresent view of the world at all times. Like a single camera can only see its current field of view. RNNs and LSTMs help the agent remember what it recently saw and how to use that knowledge to help plan its future actions. Okay, now to make sure that the DQN agent is still functioning as expected from the C++ side, we have a natively compiled sample that should confirm it's still working and show how to use the API. So this is the simple fruit example where the player agent magenta learns to home in on the fruit object in yellow. The game uses second order velocity-based control, and each frame, the DQN can choose to either increase or decrease the agent's velocity with respect to the X or Y direction. Hence it's able to move diagonally within a single frame. The agent spawns in a randomized location each episode and is rewarded based on if it's getting closer or farther away from the fruit. In about 100 episodes, the agent learns to associate the yellow input pixels with positive reward and the magenta pixels with its own position, until it's able to steer directly towards the fruit regardless of its own starting location. If the agent runs off screen or exceeds a timeout of 75 frames, the episode's terminated as a loss and it gets a large negative reward. That keeps it on task and prevents the agent from hovering or circling around the fruit just to collect spare reward. These techniques used to shape the rewards, like micro-rewarding the agent for getting closer and farther away from the object, are implemented externally to the learning algorithm and require additional user programming and experimentation for each scenario or task being learned by the agent, and are frequently necessary to use with the more rudimentary reinforcement learning algorithms, and to an extent the more advanced ones too. It's only when we apply recent extensions from the research, like hindsight experience replay, that we can reward the agents more sparsely, like for example, only when they win or lose an episode or complete a task, instead of needing to receive the micro rewards each frame. But with sparse rewards, the time to convergence typically takes much longer, as it's harder for the agents to discover their desired behaviors without being provided that additional guidance. And employing sparse rewards often requires the use of additional enhancements to the algorithm. However, these techniques are part of the learning algorithms themselves and generalize across tasks to avoid scenario-specific reward engineering and needing to tweak the rewards for each situation that the agent's trying to learn. Ideally, we'd only need to reward the agents at a high level, because that requires less coding and tweaking from the human programmers over time, independent of what scenario the agent's currently learning. Okay, now let's walk through the source code to the fruit example. So near the top of the file, we've defined a bunch of settings to the DQN, like the size of the pixel array, the learning rate, and the batch size, in addition to a bunch of other settings which you can play around with, but that we've found work pretty well in the general case. So here's where we create our fruit environment. This handles the game-related stuff like rendering and updating the environment, and we have a separate file which wraps all of that stuff up into one, not dissimilar to how the OpenAI Gym does it, just this time it's all in C++. Here's an enum which defines the possible actions for the agent, which correspond to altering its velocities in each direction. These functions are used to create an instance of the environment with different settings, and here's where it takes in the next action selected by the agent, updates the environment, and returns the reward to be issued to the agent. The render function rasterizes the pixel array into CUDA memory and resets the environment at the end of an episode. Below, there's a bunch of variables that track the internal game state and implement the collision detection that determines when the fruit's been obtained by the agent. Okay, now back in the main source file, we're going to create the DQN learner instance using the settings defined above. Then we're going to allocate tensor memory, which is backed by CUDA, that's going to be used to hold the input pixel array that's passed to the network. We're using OpenGL for the display, so we're going to create a GLX window here, along with some other stuff for the visualization. Now in the main loop, we start by getting the latest frame rendered from the environment. Then we have to do a color space conversion in CUDA that converts it from RGB video into planar BGR format, which is what the networks prefer. Now we're going to call next action on the agent, which will take in the input pixel array and perform the forward pass DQN inference, returning us the selected action from the agent. Then we pass the selected action to the environment, which will update the game and return us the reward that should be issued to the agent. We compute some statistics which are used to track the agent's progress, and then we pass it the reward, which kicks off the training. And that's it. The remaining steps of the tutorial will use the API in a similar fashion, just with more complex environments. Okay, so now that we know our agent's learning properly from the C++ side, we're going to head and integrate it into the Gazebo 3D robotics simulator and perform a couple scenarios there, including a robotic arm and a ground rover. Okay, after Gazebo started up, you can see our robotic arm, a camera, and this green cylinder object, which the arm is trying to touch. Similar to before, the agent's rewarded based on if it's getting closer or farther away from the object. If it's able to touch the object, it counts as a win, whereas if the arm impacts the ground or times out, it counts as a loss. The video from the camera is captured from Gazebo, and the pixel array is input into the DQN network, which predicts the action that the agent should make next. Now normally, robotic arms are controlled via inverse kinematics. However, the DQN agent is manipulating the arm joints directly. How this works is the code maps the actions from the DQN to control each degree of freedom of the arm. Each degree of freedom corresponds to two possible actions, one action that increases the value of the joint and another that decreases it. Hence, the number of outputs of the DQN are 2 times the number of joints in the arm, plus 1 if you want an action for doing nothing. Having that extra action that does nothing is useful if you're working in second or third order, where the agent may just want the arm to stay in motion on its current trajectory, instead of being forced to update velocities or accelerations every time step. The agent's typically limited by its number of outputs or potential actions, too many actions to choose from, and it can have trouble converging. So we start here with 4 degrees of freedom, 2 arm joints, plus a rotational base and a gripper. Now once the arm is able to touch the object somewhat reliably, we can move the object to a new location so that the arm will learn to follow it. It typically takes the arm a few failed attempts before it realizes that the object's in fact moved and that it needs to start looking around again to find it. Before long, it's able to find the object again after a few tries. And typically after it's able to find the object again, it remembers that and keeps returning to its new location. Now over time, the agent will learn to associate the green pixels in the input video with the reward, and be able to locate the object in new randomized locations each frame. Here we change the object location again, and see the arm adapt faster than it did before. Now although this is a basic scenario meant predominantly for testing, the workflow has been set up so that you can customize the simulation with your own assets and environment based on the specific task that you'd like the agent to learn. So to integrate the DQN with the simulator, we've created a set of Gazebo plugins which bridge our API with Gazebo. Here's what the main plugin for the ARM looks like. It receives the camera video and controls the arm joints from a DQN agent. Okay, now let's take a look at the rover simulation. It's not dissimilar to the arm in that the objective is for the rover to contact the green object. If it runs into the orange barriers or times out, it loses. The rover is rewarded pretty much the same way as the arm. It gets positive reward for getting closer to the object and negative reward for getting farther away. Naturally, the controls for the rover are different since it's skid steer. However, there's still discrete action mappings from the DQN that control the motors. Like with the arm simulation, we're able to move the target object around and modify the rover's navigational path. It doesn't take long for the rover to realize that the object's moved and for it to start searching for its new location. After a few iterations, the rover finds it and begins reliably homing in on its new location. So we move the object once again, and like with the arm, over time the rover will learn to associate the blue-green pixels with the positive reward, and eventually will be able to navigate to completely randomized locations every frame. The real-world analog to this scenario consists of dynamic waypoints and landmarks that the rover may need to navigate to while avoiding obstacles in its environment. If you have your own ground rover, you can take this simulation and build on it to support your own scenarios. Like with the arm, we've created a rover plugin for Gazebo that captures the camera feed and controls the rover's skid steer drivetrain from the DQN agent. It shares a lot of code in common with the arm plugin, and you can modify it to support your own environments. Okay, now to get the agent out of the simulator and onto the physical robot, we use what's called transfer learning. It's a shortcut that utilizes a pre-trained model that was trained in a similar environment or on a similar task, and adapting or fine-tuning that pre-trained model to fit the new scenario. It can greatly reduce the training time to not have to learn from scratch every time. Basically what you do is save the best model checkpoint from the simulator and then load it at runtime on the robot. It sort of acts as a more accurate initialization for the network. Normally the network layers are randomly initialized, but initializing them with transferred pre-trained weights instead gives them a much better starting point. Depending on how accurate your simulation is, you may need some degree of fine-tuning the model on the real robot itself. For that, we can utilize online learning. Online meaning in situ or in real time. Online learning is useful when you want the agent to adapt or tune its model inside the actual environment it will be operating in. Here's a video of Berkeley's Brett robot learning to assemble toy parts. Brett uses deep reinforcement learning and GPU acceleration. Typically, training is a very demanding process. However, with the computational horsepower of Jetson and GPU, it can be done on board the robot itself. Since reinforcement learning works through dynamic interaction with the environment, where the agent tries a course of action and learns a little by integrating feedback from the environment before trying something else, its learning process doesn't work offline, like if you were to simply record data and train it later statically. If it's unable to adapt and try new things at the time, it won't converge. Online learning brings its own challenges versus working in a virtual environment, where it's easy to derive the rewards and reset the simulation at the end of an episode. In the real world, to avoid human bottlenecks, we'll need to find self-reinforcing scenarios where the agent's essentially able to reward itself, for example by using a pre-trained supervised network that can recognize when the robot's won or lost an episode, or by using a higher-end sensor like a LiDAR for training that's easier to extract absolute distances from. The higher-end sensors used just for deriving the rewards and then can be removed when the training is complete. It also helps a lot if the scenarios don't require human intervention to reset every episode. For example, a robot that's roaming a seemingly endless environment like a maze or a penned-in area. We have one more topic to cover today, and that's the difference between discrete and continuous control. Discrete learners like DQN are only able to indicate one specific action of their choosing, like go left or go right. It's up to the user to map that symbolic action to a value of some kind. They can only choose one action at a time, hence they can only control one degree of freedom per time step. However, in robotics, we frequently have many degrees of freedom and would like to have the network output real value variables with an unlimited range and precision. For this, the latest research is concentrated on policy gradients and actor-critic-based methods that are capable of operating in continuous domains. Actor-critic models actually use two networks, the actor network that we're familiar with, and a critic network that provides additional feedback to the actor, enabling it with the accuracy and precision necessary to deliver continuous values. They can output lots of different values and controls simultaneously, too. Example policy gradient and actor-critic methods in the research are PPO, proximal policy optimization, DDPG, distributed deterministic policy gradients, and A3C, asynchronous actor advantage critic. There's also a GPU version of A3C, A3G, which we have an example of in the repo, running on one of the OpenAI Gym's most challenging and difficult environments, bipedal walker hardcore. In this scenario, a humanoid-like robot with many degrees of freedom of continuous control learns to walk through a hilly course filled with obstacles and pitfalls. Due to the additional complexity of the environment and continuous control, the training can take a lot longer. To offset this, many of the policy gradient and actor-critic methods are parallelized and collect experience from many agents running simultaneously at the same time. Here with A3G, we're running 12 agents in parallel on a laptop with a 1070M to reduce the training time. However, you can run it on a TX2 with fewer agents. Now, when we first start up, the robot's basically unable to walk using locomotion at all. Instead, it tries to scoot around the ground without really picking up its legs. But if we fast forward a bit, we'll see that it begins to walk under its own power until it can start to move through the course, but still gets tripped up and falls quite a lot. After a few hours of training, the agents are at times able to traverse the environment to the end, jumping over obstacles and going up and down stairs. In the future, we plan to add more of these continuous learners to the repo and into the API so they can be used on real robots too. Well, we've covered a lot of ground today, but this is really just the beginning. There are new deep reinforcement learning algorithms being published practically every week in the research. We plan to continue updating the repo from this tutorial with the latest techniques and examples for you to work with. Visit these websites to keep up to date with the latest available from NVIDIA, including the Isaac Robotics SDK and Jetson XAVIER. With that, it looks like we've reached the end of today's presentation. Thanks again for joining us today. Here are links to the resources mentioned that you can access anytime. Now we're going to take questions and do Q&A. You can type any questions you may have into the chat box in your webinar viewer. If we don't get to your question, please feel free to post them to the forum and we'd be happy.
Okay, so anybody that has questions, please type them into the Q&A box and we'd be happy to answer as many as we can here. If we don't get to your question, please post them to the forum and we would be happy to answer them then. Here's a question: can you implement RL on Jetson using TensorFlow? The answer is yes, you absolutely can. There's a lot of TensorFlow code out there, and you can install and compile TensorFlow natively on Jetson. We have a couple threads on the forum about doing that. For this tutorial, we just chose to use PyTorch because it's a little more straightforward to use on Jetson, and the performance is slightly more optimized and less overhead. TensorFlow does have an advantage of being slightly more popular and having more reinforcement learning algorithms implemented, but they're essentially quite similar in functionality, so you can use both. Here's a question: what was DQN again? DQN stands for Deep Q Learning, and it was an algorithm popularized by DeepMind to beat the Atari and other video game simulations. Since then, the research community has moved on to more advanced learners like DDPG and A3C and PPO and the more advanced continuous reinforcement learners. But DQN is still very good to start at, especially when you're implementing a new architecture. Here's a question: can you talk a little more about A3C versus A3G? So A3G is basically just the GPU accelerated version of A3C, which stands for Actor Advantage Critic, or it's one of these continuous reinforcement learning methods that are highly parallelizable. And basically, it's the same algorithm. It's just that the neural network and actor simulation is all accelerated on GPU. And there's a couple of different GPU versions of A3C floating about. There's the A3G and then GA3C, which is published by NVIDIA. They're essentially a very similar thing, and you can find various implementations of those on GitHub. Here's a question: can RL be useful for non-robotics use cases like game playing? And the answer to that is definitely yes. In fact, it was one of the first applications for reinforcement learning was game playing, and that's kind of where deep reinforcement learning came about. Was before the OpenAI GYM even came, was published by OpenAI. There was VizDoom environments and other Atari-based Zentari simulators and stuff. So that's really where a lot of these algorithms were developed to play games. And now we're playing StarCraft 2 and other advanced learners like the AlphaGo and such. But now we're applying those to robotic platforms. Okay. Can you use Jetson TX2 for training a deep neural network? The answer depends on which network. Generally, the big ones like ResNet52 or GoogleNet, those are best trained on a discrete GPU like the Titan X or whatnot, because those have huge amounts of layers and are very complex and are generally trained on many terabytes of data like ImageNet, for example. But with reinforcement learning, if you noticed in the code, the deep reinforcement learning networks are somewhat more simple, and all of the data is generated in real time. So TX2 you definitely can use to train smaller networks and is adept at doing real-time simulation. It's just a matter of the speed that you require, and certainly you can speed it up on higher-end GPUs if you have access to those. TX2 has the advantage of actually being able to be deployed to your robot, so you can do online training on board the real robot. That's kind of why we built it around this architecture, to confirm that you can do all the same training with the same code and not have to completely re-architect your solution. Let me scroll up here. So will Isaac be integrated with ROS? That's a good question. We are going to provide a ROS compatibility layer with Isaac that you can use to take Isaac processes and wrap them as ROS nodes, or vice versa, take ROS nodes and import them into the Isaac data stream. Here's a question: does PyTorch work on x86, and does this repo work on x86 with NVIDIA discrete GPU? And yes, you can compile and build this GitHub on x86 also. And as long as you have an NVIDIA discrete GPU in there, since all of the code provided makes use of the CUDA extensions in PyTorch, it'll run just the same. And here when I'm developing it, I run it on both the Jetson dev kits and on a laptop as well to confirm that it both works. Here's a question: is Gazebo free software? Yes, it is open source, free simulator, and came out of the ROS ecosystem, but is now split off into its own project, and it's completely open source. PyTorch is completely open source. Our repo for this webinar was completely open source, so it's all free software. Let me scroll up a little bit. Here's a question: what is genetic pruning? I didn't really have time to cover that in the slide, but basically what it means is that you run a bunch of agents in parallel, like A3C, but then choose the agents that get the best performance and continue on with the training of those and potentially combine them together. One thing that these parallel learners like A3C and A3G do to synchronize the learners together is that they can basically average the weights of the network to combine multiple agents. So you run lots and lots of agents and pick the ones that perform the best, then average those weights together, keep doing that process over and over again until you get the best possible agent over time. So that's what genetic pruning is with respect to reinforcement learning. How compatible is PyTorch with TensorRT for Jetson at the moment? The next version of TensorRT, TensorRT 4, which is currently available on desktop and will be available in an upcoming version of Jetpack, that includes support for ONNX, ONNX, which is a standardized neural network format that a lot of different frameworks support, including PyTorch. And so you'll be able to import PyTorch models into TensorRT, just like you can do with TensorFlow and Caffe and a bunch of other frameworks now that ONNX support is coming. Okay, let me find another question here. There was a question about how can I be notified about the Jetson XAVIER early access. There was seems like they were confused about the form. If you fill out the Notify Me form in the link provided through the webinar viewer here, that will allow us to send you information about when the early access and general access for XAVIER will be occurring in August and October of this year, respectively. Here's another question about XAVIER. Are we going to be releasing the design of the Jetson XAVIER dev kit carrier, like with TX1 and TX2, because those carrier boards were completely open source, and you could use our design to make your own carrier and enclosure solution? And the answer to that question is yes, we will be releasing the same design collateral for the XAVIER dev kit, and you can download that just the same. Okay. Are there any versions of Inception neural network used for DQN? And the answer is yes, people have started to use Inception, or commonly referred to as GoogleNet, interchangeably, and ResNet as well. Some researchers here at NVIDIA have been using ResNet with, not with DQN, I don't think, but with DDPG and some of the more advanced ones. But yes, they have started adding and making the neural networks and reinforcement learning much more complex to add to its recognition capabilities. And I think you'll see more of that in the future. Okay. Here's a good question. How can you incorporate human player input into training models in the simulations? And this was one of the last bullet points that I had on the closing slide about supervised seedings of networks, where the human could control the robot for a bit when it started up to produce a better than random initialization of the neural networks. And basically the way that would be done is very similar to the NVIDIA DriveNet style of network, where you can train a self-driving car by having a human driver drive it around and record all the data and then train the network. But then after that's done, you can have the reinforcement learner take over, so it will have a much better initialization than just completely random. Okay, maybe you have time for one more question here. How can fine-tuning be applied to a real robot? And the answer is, the software stack presented in this webinar is basically geared entirely so that you can take the simulation and then transfer it to the real robot without really having to change the code to make that amount of fine-tuning minimal. And the reason for that is because you don't want to have to stand by the robot and manually train it every single time, although it should only take a few hours to do so. So it's not completely unheard of. But if you were to enable a scenario that was self-reinforcing or automated, then the robot could essentially train itself overnight or just keep doing it. And the way you could do the self-reinforcing is have other sensors monitor it, or use a pre-trained network like Inception or GoogleNet to recognize from a camera, when the robot has succeeded in its task. Well, there was a lot of questions. Unfortunately, we didn't have time to get to them all, but thank you for submitting them. And if you have a question that didn't get answered, please post them to the forums or social media. And we will post the video of this webinar shortly after the presentation, so you can watch it or share it again. So thanks again for joining us.
Thank you all for attending today's webinar, and thank you, Dustin, for presenting. As Dustin said, a recording of this presentation along with the slides will be available shortly on demand. You'll receive an email with a link to this information later today. There's a lot of questions that we weren't able to get to, so please make sure you check out that webinar forum thread, and we'll keep the conversation going there. You can find a link to the forum in the resources link to the right on the webinar portal right now, or it'll also be included in the follow-up email. So thanks again for joining us, and we look forward to you being with us at our next event. Have a great day.